Hi, welcome. This week we're talking about this model that was in Nature. This article, Solving Olympiad Geometry Without Human Demonstrations. Uh, this is not too technical. It's not a super mathy discussion. So I think we can go through this and take time to see if people have any questions about how this thing works. Um, and hopefully, yeah, have a pretty good discussion. So feel free at any time to put questions in the chat or ask questions, pause me, raise your hand, whatever, all the above work. All right. AlphaGeometry is the name of the model, and they built this over at DeepMind. So here's the overview, okay? So this is not all math problems. It's not even all geometry problems, okay? There's this particular subset that they looked at, Euclidean plane geometry. And the idea is to actually do proofs. Prove that if you're given this triangle and this circle and these points and then these two things are equal or whatever, something like that, right? Um, and what they did in order to get the computer to do these proofs is that they took symbolic deduction engines, which already exist. This was not something novel, interesting. These are like off the shelf things that you can use. Okay. And what this symbolic engine does is it'll take your list of facts and it'll have certain theorem premises, right? So, like, if you have a triangle and you have two of the angles, then the third angle is going to be 180 minus the sum of those first two angles, for example, right? So
Mhm.
then basically if you have that as one of your theorem thingies, then if you're given, and by the way, usually geometry problems don't have specific numbers, but I'm just like trying to say, for example, right? So if you're given two angles that are like 45 and 45, then basically it's going to say, oh, I have a new fact, which is that the third angle is 90. Okay. Um, and so then what they use deep learning for, they use an LLM to suggest new objects to construct. So adding points, bisecting an angle, putting a circle inside of a triangle, putting a circle outside a triangle, taking 3 points that currently are a triangle and adding a fourth point to make it a parallelogram, all those kinds of things. Okay. Um, and this space of auxiliary construction is pretty huge. Like there's a very large number of things you could do each step to add to your already existing sets of points, lines, triangles, whatever. I thought it was interesting. The paper actually says the infinite space of auxiliary construction, and it's kind of like, well, it's very big. I don't think it's quite infinite, but it's very big.
Infinite sounds better, though.
It does. It does. And they're like, we
Mm.
solved the infinite auxiliary construction problem. Um, so then uh, that's how they wanted, the architecture for what they want to do. But the big problem is you're going to need to train this thing. And there's very little data, which we'll get into. So they solved the training problem by finding a way to generate their own synthetic proofs and creating the training set. So they train the LLM on a whole bunch of proofs, and then they fine tuned it on the subset of proofs that specifically required at least one step of auxiliary construction where you add a new point, you add a new something. All right, so that's the high level big picture. Does that make sense? Any questions?
One, Ted, I don't know if you're going to go into this, but for those that aren't familiar, could you explain the mathematical Olympiad?
Mathematical Olympiad. I would be happy to. Uh, so so since I think like 1950, there has been a competition for young mathematicians, for high school math students. And I'm sure it's evolved over time, but for the last like 30 years, the structure's been that when you're in high school, you can take this uh, uh, math contest in the United States. Every country, does whatever they do. Um, uh, and I don't know if it's still called it, but it used to be called the American High School Math Exam. AHSME. And if you do well on this test, then they invite you to take an even harder test. So then they invite you to take the American Invitational Mathematical Exam, so the AIME, the AIM. If you do really well on that test, then they invite you to take the final public level, which is the U.S. Mathematical Olympiad test. All right. And so, by the way, I've taken all these tests, so this is why I know about all this stuff. Okay. Um, then what they do in the United States is they want to do well in the international math competition, right? Each country sends a small team to this competition. Uh, so we actually have a U.S. Mathematical Olympiad training camp, just like the U.S. Olympic bobsled team has a training camp, and the U.S. whatever. We have like a mathematical summer camp. Um, and so the way they do that has changed a little bit over time, but basically it's kind of like the top 12 people are the people who they think are the true candidates for the US math team. But they usually have something like, I don't know, 30-ish people that they invite to the camp. So if you don't quite make the grade, but you're younger, you're, like a sophomore or something, then they'll say, hey, come to the camp and we'll do workshops and whatever. And maybe next year you'll do better and you'll actually be in the top 12 or whatever. Really, really funny trivia. My wife really got a kick out of this. Um, they've always had this test amongst the 12 people to see who was actually going to make the Olympic team for the United States, right? And so this is the team selection test, the TST. And at some point, I can't remember, like 10 years ago, there was a controversy. It's like, well, we got 30 people in the camp, but you only let the top 12 people take this test. Shouldn't you just like everybody and like if they do well, right? But they're like, well, maybe we'll just get lucky and do well in this one test, but they won't be the strongest person on the team. But what we will do is we'll create another test, and if you do well enough on that, then we'll let you actually try the team selection test. And so they called it what did they call it? The team selection test, right? The team selection test or whatever. So it's just this like ridiculous name. So it's instead of the TST, it's the TSTST.
Oh, they didn't spend a lot of time working on that name.
No. So I've talked to my wife about this. She thought that was just this the silliest, stupidest name.
I'm with her.
All right. So anyway, so then you choose a team, and then they go to the International Math Olympiad, and they try to do these crazy hard math problems. And so this is like yeah, like US Math Olympiad problems. I don't know what it is like. The average is, I don't know, you can do the numbers, but it's like only 5% of people get invited to the AIM, and then of that, how many percent get invited to the US Math Olympiad and how many do well, whatever. And so it's like a fraction of a percent. So these are pretty hard problems. And the international problems are even harder. So yes. So so once LLMs got to the point where they could do sort of ordinary word problems, and this is pretty recent, ordinary word problems that you and I can understand. Like, Sally went and had 6 apples and she gave away 3, and then she bought 4 more, and then someone doubled her apples. Like, how many apples does Sally have, right? We can finally do those. So to keep pushing the envelope, now people have been working on different mathematical Olympiad problems. All right.
Thank you.
You got me
Thank you for
started,
the
Jerry.
sidetrack. Yes.
Yes, you really got me
No,
down
no,
the rabbit hole.
I was trying to figure this out in my mind, and I had a completely different picture of it. So appreciate that.
Oh, now I got the acronym right. There's the team selection test. So it's the team selection test, selection test. Okay. All right. Anyway, that's not what we're here for.
The whole thing sounds a lot like American Idol. Like you got the semi-finalists and you got the semi-finalists.
Yeah.
So Alan, I don't know if you know this, but like in the United States, there's this like known thing, like you have this like 10-year-old playing Little League baseball, and there'll be the parent that's like super into it and like yelling at the coach and like my kid doesn't get enough playing time and all this kind of thing. And I'm actually just envisioning like these crazy parents of math kids who are like that, but about my kid didn't get a chance to take the team selection test for the International Math Olympiad, as opposed to, my kid didn't get enough playing time at, second base or something like that.
Yeah, yeah.
Okay. Um, so let's first talk about the symbolic deduction engine. Okay. So this is nothing new that DeepMind developed. Okay. So the symbolic deduction engine for geometry has a database of geometric rules, and they added a component, which if we have time at the end, we can talk about the algebraic rules. So the geometric rules don't really deal with numbers in any way. Okay. You just have the idea of like equal and whatever. And then there's certain kinds of geometry problems that they didn't include in this. So I believe there's no like less than or greater than in this type of geometric problem. There's only like equality and things like that. So all the rules that are in here are of the form, you have these different propositions, okay? It could be one, it could be multiple things, but up to k different propositions. And if they're all true, then you know that this thing Q is also true. And so then basically you can take Q and you can add it to the list of things that you know that are true, right? So just to give you like an example, so if you have two parallel lines and one line's AB and the other line's CD, okay, then the X for that might be A, B, C, D, 4 points, okay, with the understanding that the first 2 points have to describe one line and the second, to describe another line, okay? And so if A, B, and C, D are parallel, that could be a particular proposition, okay? So you'd have P1 parallel parentheses A, B, C, D close parent, right? And then you could have some other, propositions about points that are on the same line, whatever, angles that are equal, all these kinds of things. So that's how basically this symbolic deduction engine does like matching on things, and it can find a match. Then it basically adds one more thing to the list. And so each time you add a thing to your list, then there's more things that can match various rules. And so it'll just keep going until it finally can't match anything. And so it'll go and it'll compute the closure of all possible things based on the theorems in its database that you can prove given a certain set of initial starting point premises. So the thing to know is that this symbolic engine can actually solve some of the simpler problems at the International Mathematical Olympiad. So you can think of this basically as like you have an open book exam where you have access to every theorem in the geometry book, and you're really fast at comparing every one of those theorems to whatever they gave you on the sample problem. That's essentially what the symbolic deduction engine do. Okay. And they said in the article that these existing techniques, like generally speaking, would run in a matter of just seconds on the kinds of problems that they have in the International Math Olympiad. So this is not something that you really have to worry about optimizing or whatever. You just, bang, you run this thing. So let's talk a little bit about what that might look like. So forgive me, some of you this may be like really obvious, but whatever. So I tried to come up with an example. I don't necessarily remember my high school geometry, but I kind of remember this whole thing about you have two parallel lines crossed by a transverse line, right?
Yeah.
Okay. So let's say you want to prove that angle 1 over here that I have in red, and angle 6 over here in red down here are supplementary, given that AB and CD are parallel lines. So what the symbolic engine might do is say, oh, I've got some whatever theorems that tell me that angle 1, 4, 5, and 8 are all equal to each other. All right. And then it might also say like, hey, here's a line EF, okay, and 6 and 8, like, combined, form the whole line. So 6 and 8 are supplementary, right? And so if 1 equals 8 and 6 and 8 are supplementary, then you know that 1 and 6 are supplementary. QED, we're done. Okay. So that's what the symbolic engine can do. But let's look at an example of something the symbolic engine can't do. Okay. And again, I don't know if I got all the geometry right, but just, roll with it if I have something slightly off. So you have two triangles, ABC and ABD. Okay. So they share this common side over here, AB, right? But the first triangle is just the part on the left, ABC, and the second triangle is the part on the right, ABD. And you know that lines AB and CD are parallel. And we want to prove that these two triangles have the same area. All right. Now, maybe there's some other technique that you can do this, whatever, but like my simplistic brain says the area of a triangle is 1/2 base times height. Okay. So the only way to solve this problem is you have to do auxiliary, well, the only way I know how to solve this problem is you have to do auxiliary construction. And so you have to add 2 points. You have to add P1, which is perpendicular, that allows you to calculate the height of triangle ABC. And you have to add point P2, which is perpendicular and allows you to calculate the height of triangle ABD. And then somewhere, I don't even know where, but I assume there's some theorem that says that if you have two lines perpendicular to the same parallel lines, then they're the same, right? It seems intuitive to me, but I don't remember. So then, if you know P1 and P2 are the same length, and you know that both triangles share the base AB, then 1/2 base times height will be the same for both of them. But this can only be proved, again, in my made-up example, by adding not 1, but 2 points. And they're very specific points, right? They're the points that, like, a perpendicular line dropped from C, intersects AB, and a perpendicular, right? But basically, you have to add 2 points in order to solve this problem. You cannot do it with just A, B, C, and D. So does that make sense in terms of like, hey, here's a kind of problem that's harder because you have to figure out what do I need to add to this and the possibilities of adding things. We could have added points in lots of other places, or we could have added things other than points,
Mm-hmm.
We could have said, oh, add a point that is on the segment that bisects the angle ACB, or add a point that's the midpoint of AB, or God only knows, some kind of, center of mass of the triangle. Well, whatever. There's lots and lots and lots of different things we could have done.
So Ted, quick
Yeah.
question. So is the idea that the existing systems are not able to generate these additional points because it's intractable? There's just too many additional constructs that you could add.
That's right.
Okay.
That's right. Yeah, I mean, you could take your symbolic engine and you could just give it extra rules that let it do it. And that's basically what some people have done. They have these heuristics. And so they'll say the heuristics will allow these symbolic engines to add certain things. But because they're just generic heuristics that are not context specific, you can only have so many of them, or else the space explodes combinatorially very, very fast.
Gotcha.
Hi, Ted.
Cool. Yeah.
Hey, Ted. Hey, a quick question. Sorry, I missed the beginning of it. So, what is input to the model? Is it this diagram and the fact that, CD is parallel to AB, or what is input?
Yeah. Yeah. So I haven't really explained it, but basically, what will be input to the symbolic deduction engine is just the things that you're told in the statement of the problem that are true. Okay. So, like
Okay.
in the case of this, you're told that you have 4 points. That's the first piece of information. You're told that the line AB is parallel to CD. That's the second point that you're told, right? And then you're told that, I think that's pretty much it. You're just told that, I don't know if you even have to be told, but that ABC is a triangle, ABD is a triangle. And then it says prove that the area of ABC equals the area of ABD.
Right. Okay. Yeah.
And I'll actually show you what that looks like, some examples of what that looks like. But basically, that's what the symbolic engine gets. We haven't gotten to the LLM at all yet.
Right. And so there's so much other stuff going on in terms of like saying that the two triangles have the same base.
Oh, sorry.
That
Yes. No. Well, actually, no. If you know it's ABC and
right,
it's ABD, that
right.
they share a side is implicit because they're
Correct.
named ABC.
Right. So I'm saying that there's other stuff that can be gained out of that that I don't know if
Yeah.
it's
Yes.
gaining it
No.
and so
There
on.
will be a lot of other things. Like, I mean, hypothetically, you could have uh, something that says these three angles, right? CAB, ABC, and BCA will sum to
Mhm.
180 because that's just fundamentally true about any triangle,
Right. Right.
right? And then I'm sure there's some version of that where you're like, oh, but I can actually use like BCD on the right instead of CBA. And, yeah, so there's going to be like hundreds, if not thousands of things just from this input that you
Hmm.
can prove,
Yeah.
all about this small little situation.
Yeah. Cool. Thanks.
There was a raised hand, but it dropped. Anything else? Okay. So let's keep going because I know I haven't actually explained, but I just wanted to make sure we understand sort of what the symbolic engine does. And that's coming to us just as a freebie. Okay. These already exist. Just there's multiple of them. I've never used any of them, but the authors are like, hey, there's different ones. Okay. So perhaps the biggest problem that they had is like we know that, well, if you can have like internet sized training data, you can train language models to do pretty amazing things, but we don't have internet sized training data about geometry. There's very few geometry proofs, and there's problems translating them into something. Apparently there are like general purpose mathematical languages like something called lean, but lean doesn't specifically do geometry, and so certain things are hard to express in it. And then there are geometry specific languages, and each can do some things, but not like every possible thing in geometry, and blah blah blah. And and so with what's out there right now, you would just say, okay, I hand collected 150 proofs. Now I'm going to translate them to this language. It would be very time consuming, and you still would not have a very large data set.
Mhm.
So ultimately, they said, if we're going to solve this problem, not only do we need more than the human proofs, but we're actually not even going to use them at all. We're not even going to bother with them. We just need to find another source that's big. And so what they did is they said, we're going to create our own synthetic theorems and proofs. How are we going to do this? So first, what they do is they sample some random theorem premises from all the different possible things. Okay. Um, and so then basically you have a theorem premise that says, whatever, given two parallel lines and a line crossing it, then this angle will equal that angle, whatever, right? So then basically you say, okay, so now I'm going to assume that I have those inputs. I have the two parallel lines and the line crossing it. Okay. Uh, and then let me just add this next theorem premise. And so based on that, uh, I now have more objects, and now I can say, what are all the things that I can prove are true, given this like bigger collection of objects, right? And so they just keep adding things that they know that are true, but for each one, what they do is they keep track of how they got there. And so they will have basically a directed graph which shows what you started with, and then each time you use a new rule to add something else that's true, then the new thing will sort of like be connected to the things that it needed. Okay. And so ultimately this will keep going and it'll get bigger and bigger combinatorially, but you'll get this directed graph of things that you know are true. If you build a graph like this and then you randomly pick a node somewhere in here, probably not one of the ones that you started with. Okay. So let's call this node N. All right. So this node shows something that we now know is true. We can trace backwards through this graph to find the minimal set of premises and the minimal set of rules that we needed in order to prove this particular thing N is true. Okay, so N could be the two triangles ABC and ABD have the same area. Okay, so then what you do is you work backwards to say, well, what did I need in order to prove that those two triangles have the same area? And so then you have this small subgraph. And then basically they say, yeah, so if you look at the premises you needed, you call that set P. You look at the conclusion, which is your node N, these two triangles have the same area. And then the whole subgraph, all those other, edges where you added different deductive steps, that's your proof. And so this is now a synthetically generated proof. Not all proofs are interesting, okay, but this is a synthetically generated proof. Any questions about this? I have a diagram coming up, so that might help. All right. So you start with some random things. I've got a bunch of points. So here there's what, like 8 points, and you've got some additional info that says certain things are perpendicular, right? Like CE is perpendicular to AB, whatever. So here's my premises. And now I'm going to prove some other things here, okay? But for everything that I prove, I'm always going to have an edge that I keep track of, like, where did it come from? What information did I need? And so they show whatever, I guess you can prove that AH extended until it intersects is perpendicular to BC. Yeah, it's a hand raise, Shilin.
Yeah, is that kind of like a formula sequence? So this is like the cycling EADH is our like sentence 1, and EAH equals to EDH. That will as our kind of like that sentence 2. So there's kind of like we are forming this kind of like a sequence. So that's why it fits the LLM model.
Yeah. So every sentence or every fact is going to be a node in your graph. But what they're doing is they're always making sure they keep track of which things they used in order to prove that. So they're saying this HA is perpendicular. Where's my mouse? HA perpendicular to BC had 3 things that were necessary. So you see these 3 arrows that are coming from it. Okay. And it's only if they have those 3 things are they able to prove this is true. So the minimum proof for this HA is perpendicular to BC would be our conclusion, what we called N. The graph of the things that you need would be G of N, that would be the proof. And then the set of starting point premises would be your initial conditions, your P. So in this, where I say the initial premises are P, all the different steps to prove it. Oh, sorry, this is your conclusion, which is just whatever statement was at the end, and then the proof is the whole graph.
Thank you.
Hey, Ted, one other question.
Yeah.
So as we're looking at these, they're geometric problems, and we have pictures drawn that we use. Is this model looking at the pictures at all, or is it just textual descriptions of the premise, etc.?
Yeah. So the symbolic engine, we're only talking about the symbolic engine so far. So we haven't even gotten to what they did, because this existed before they even started this problem, okay? But the symbolic engine is only seeing the facts written in a specific layout. And they did actually build a routine to draw these, because it's a lot easier to debug what's going on if you can see a picture of it. But the picture is really just for us. It has nothing to do with how the computer solved the problem.
Interesting. So we think visually, and so we needed the pictures to get through it, but it's just using the text.
Yeah, exactly. And I'll show you in a second what that looks like.
So wait, Roger, or maybe Ted, this is actually storing these as text?
Yeah, and of course it has some very specific text, like is parallel ABCD, means that the line AB and the line CD are parallel.
Okay.
Okay. And maybe there's a thing called is right triangle ABC, and there's a specific order you have to list them so that like the right angle is always like the second one or the first one or what, you know what I mean?
Gotcha. Yeah.
Like,
So
or
this
is
is what they be.
isosceles triangle, you always have to list the two that are the same, like, you know what I mean? So there's a very specific layout to each of these facts, but
So
once,
if we were thinking about it from a language model, the grammar is fairly tightly controlled then into how you construct these things.
yes. Yes, and if you imagine like any function in Python that takes 3 parameters, you can't change the order of the parameters. You have to make sure you're always
Absolutely.
passing them in this specific order.
Okay, thank you very much.
All right. So this is how we've generated some proofs. The next step, what we want is we want proofs that require auxiliary construction. So this part I'm not 100% certain on, okay? But the idea is you start with one of the proofs that we just talked about. You have a bunch of facts you start with, a bunch of graph steps where you add new, facts. And then, sorry, I keep saying in the wrong order. You have the conclusion that you want to achieve at the end, and then you have the proof, which is the list of facts in the order that you derive them. If there is a subset of P that your conclusion N is independent of and can be removed, then what you can do is you can remove those from the list of premises and instead make those auxiliary construction steps. So I'm not 100% sure about this, but I think you can think about our points P1, P2 from the triangle area example, okay? So basically what I'm saying is if you got a proof that said, in this situation, you know that the two triangles areas are the same because 1/2 of AB times CP1 equals 1/2 of AB times DP2, okay? So if you had that proof, that's a very trivial proof. But you'll notice that the definition of it is like, hey, the triangle area ABC and ABD, but they never mention P1 or P2. So they're saying when your sort of conclusion is independent of certain things like points P1 and P2, what you can do is delete them. So we're going backwards now to this looking initial set of conditions, which will then force the proof to create P1 and create P2. So that's what they do is they found a way to go backwards. They found a way to say, I have a proof that does no auxiliary construction, but I found that certain points are not part of my conclusion. And so I can then delete them and then, make the proof use auxiliary construction to add them back in, so to speak. So it's a lot easier to work backwards than it is to work forwards. Okay, it's much harder to do a proof. But if you have a complete proof, then you might be able to say, I can sort of remove these parts of it and force you to actually build them in order to make the proof. Does that make sense? So that's the process they use. They build a whole bunch of proofs and then they go backwards, removing some things to make the proofs harder. And so now they have a set of harder proofs that require auxiliary construction. Okay. It turned out that they had lots of duplicates and things, but when they one second, when they deduplicated, they got 100 million proofs, and only 9 million of those, 9% of them, actually required auxiliary construction. Yeah, sorry. Please ask your question.
Oh, no worries. Yeah, I just wanted to add, this is how even code training was done by Code Llama, where they had the previous and the end part and fill in the blank, like, take the middle out and try to fill that in. Is that somewhat similar to that, right? In conceptually trying to...
Actually, that's a good point. Or even like BERT, mass language model, right? The thing is, in BERT, you can just delete any word token and have the model try to predict what it is. You cannot in this proof remove the point A from your premises, because the definition of the conclusion is triangle ABC equals triangle ABD, and if there's no A, you don't have a triangle.
Right.
There are
So they
certain
may
things
have
you're
to be.
not allowed to delete, but anything you can delete, that's what they do.
Right. Right.
All right. So this is then how they built a training set of 100 million proofs, some of which are the harder kind that require you to have things. So if you look at this diagram that's in the article, it just shows that basically some of these proofs are very easy. It's like one step, okay? And so the x-axis here is how long the proof is, okay? So you have a whole bunch of like super short ones and whatever. And so then they're saying that in these international mathematical Olympiads, like you've got proofs that are like length 112, and then the longest problem that they solved from an actual international competition was from the 2019 competition. It required 187 steps. And then the longest proof in their training set was 247 steps in order to prove what was originally asked. Now, remember, these steps are very, very small steps, okay? But still, it's a long proof. So this is just to show that like they generated synthetic proofs and that they had some good variety here. Okay. There's some other things they commented on in terms of like, hey, if you go to like a geometry textbook, do we see the things that were in the textbook? And it's like, yes, we saw a lot of them, but not all of them. So they're saying that by no means, because remember what they did is they like just randomly sampled some premises. They didn't have any heuristic, any logical way of generating the various conditions. So they didn't necessarily pick the most interesting situations, and that's why they didn't end up recreating. I'm sure if they spent longer, more random seeds, more whatever, they could eventually generate more and more of your like typical high school geometry textbook. All right, so now we get to the ML part, the language model. So they used a pretty typical GPT style decoder only LLM. It's not that big, okay? So it's 12 layers. The model dimensions 1024, 8-way multi-headed attention. Very typical, the MLPs expand 4 times. So from 1024 to 4096. And they use ReLU. They didn't use anything fancier. No GALU, Swish, Swiglu, anything like that. The LLM had a max sequence length of 1024. Nothing huge, nothing whatever. And so this is 151 million parameters. So I think that's pretty comparable to GPT-2. Nothing huge by modern standards. One thing that makes their life a little bit easier is that with this custom tokenizer that they built, the vocabulary size was only 757, right? So typically in a language model, you're talking about 30,000, 50,000, 100,000 size vocabulary. So you probably have like all the letters of the alphabet for points, and then you have, right, triangle, rectangle, parallelogram, circle, so 700 is not tiny, but it's still a lot smaller than 30,000, which I think is like what the vocabulary for GPT-2 is. So we talked about a proof has all your starting point facts, your premises, the conclusion you're trying to prove, and then a sequence of steps. And so they just concatenate all that into a long string, and that's the training example for this model. So they trained this LLM from scratch. This is random initialized. They're not using anything pre-trained. They're not doing fine-tuning. They're starting from scratch on this. You kind of have to because it's a custom tokenizer, a custom vocabulary, okay? And they train it in the usual way. If you're curious, they do say like what their learning rate schedule is and blah, blah, blah. But it's everything you normally do where you're just doing next token prediction, cross entropy loss, 100 million synthetic proofs.
Is this your,
yeah.
Sorry. Is this your plain Jane transformer then that they're training? Nothing.
It is. It's just a decoder-only GPT-2
Okay.
kind of a model.
Thanks.
Yep. There's some other details. They used dropout, and I think they used more dropout than is typical when you're training a language model like Llama or GPT-2 from scratch. But architecture-wise, it's just a plain Jane transformer. Yep. So they trained 1 million proofs for pre-training, and then they did do a fine-tuning step. And what they did is, in the fine-tuning, they only used the 9 million proofs that require auxiliary construction. The reason for this is because, if you recall in my opening, the role of the LLM is to suggest auxiliary things to add. Once you've added something, they run the symbolic engine, and it might churn out hundreds, thousands of facts that it now knows are true based on just that one thing you added. Okay? The LLM doesn't need to do any of that. The symbolic engine is doing all the heavy lifting. So when we talk about like, hey, do LLMs do like reasoning or whatever? This LLM is, how do you say? It's definitely doing some, I'm just going to cheat. It's definitely doing some thinking, but it is not doing geometric deduction that says that A is perpendicular B is P perpendicular C, then A and C. Yeah, it's not doing any of that kind of stuff. Okay. What it does, of course, need to know some of that in order to make these good suggestions of what to add. But fundamentally, when you run this in inference mode to do a proof, the only thing the LLM needs to say is, hey, I think you should add a point over here that's halfway between A and B. Hey, I think you should add a point over here that is perpendicular to whatever. Hey, I think you should add a circle over here. That's all it actually needs to do. Now, in order to do that, you can argue it needs to understand a lot of things. But just to be clear, its role will be simply to say, add one thing to the set of things you have. And then the symbolic engine is going to go and run with the new set of facts. Yes, hand raised.
Yes. So you're saying that when you're pre-training this LLM, you're giving it the premise, conclusion, and the entire proof, not just the next stage in reasoning of the proof?
The entire proof that you need to get, yeah, from the premise to get the whole to prove that conclusion is true.
So even though it seems like during inference, it's only suggesting like one step in reasoning at a time, you're pre-training it with the entire proof?
That's right. So the pre-training is, you could liken it to geometric understanding.
Mm-hmm.
And then the fine-tuning is about suggest one addition to what I have. Okay. So likewise, you could say that if you use GPT 3.5 to do sentiment on Yelp reviews, right? The pre-training taught it everything about language. At the end of the day, when you fine-tuned it, you just wanted to output positive or negative. So it really didn't need a lot of the things that it was pre-trained on, right?
Yeah.
In the same way, when it's just suggesting one thing to add, it doesn't really need all of those other things, but it needs it in order to just understand its environment. In this case, it's geometry as opposed to, say, English language. All right, so let's actually, I've mentioned inference. Let's really rigorously go through it. Whoops. Okay. So how do you then, once you've just taken on faith that this LLM's been trained, okay, how do we actually prove something? So what we're going to do is we're going to alternate between the symbolic engine and the LLM. The LLM starts with the prompt, just here's my premises, here's what you're telling me to prove, the conclusion. Okay. You're going to run the LLM in inference mode until it basically says, I want you to add this one thing. So it might say, construct a new point X so that ABCX is a parallelogram. Okay. Now, the LLM isn't that brilliant at picking the right thing you should add. So they did a beam search, but it's a very wide beam search. So the results that they report in Nature are for a beam width of 512. So they kept the 512 best or highest probability completions of what to add. And they also, I had to think about this for a minute, they also did a beam search max depth of 16. So they would actually let the model play on past adding the first thing. They would let it add 16 things. And then after it's added 16 things, they would then say what were the most likely first things that were added and throw away the other 15. So there's a lot of work going into add one thing, because you're really saying, I'm going to, in parallel, test 512 different things that I could have. So you need a pretty fast computer to do this, because you're doing, God only knows, right? At least like something like 512 times 16 inference passes, or whatever the math is. And then you're picking the top 512. And so if you started with just points A, B, C, D, you started with just 4 things, okay? Now you're going to have 5, because each thing's going to add just one thing, all right? And then for all 512 of those situations where you now have 5 things, then you're going to run the symbolic engine, and you're going to say, give me a closure of everything you can prove now that you have 5 things. If any of those things is the conclusion that we wanted to prove, then our proof is complete. We're done. If not, we need to iterate. So then the LLM will take, it started with just the premises and conclusion. We're going to concatenate the thing that we added in the last step, whatever it told us to construct. And now that our prompt's a little bit longer, now we're going to get it to run again. So when I first read this paper, I was less impressed by what the LLM was doing, because I mistakenly thought that the LLM got to see this deduction closure from the symbolic engine. So it's like, oh, if you can see all of those facts, like suggesting something to add wasn't to me as impressive. It's still cool, but it wasn't as impressive. But I realized rereading it that A, that's not how it works, and B, it really wouldn't be practical, because the deduction closure could be like 10,000 things that you know are true, many of which are kind of trivial and not very interesting, but nevertheless, it could be like thousands of things. And so you can't really reasonably fit this into the LLM until we have some breakthrough. And so if you say, yeah, my LLM accepts, context length up to 500,000 and it can attend to all of it equally well, then yeah, fine. Then you could have done that, and it probably would have worked way, way better. But in this case, it's actually suggesting things it can keep track of everything it's added, but the next thing it suggests, it's really suggesting blind, not knowing what this deduction closure is. So I'm actually a little bit more impressed with what the LLM had to do on second reading, once I realized, oh, it can't really see that. So what I would say is, even when you're like only one step away from the proof being complete, it's not necessarily clear that the LLM would know that you're close, because it can't see all the other things that the symbolic engine is telling you it are true. So, all right. So here's a picture from the article of what this proof-solving workflow looks like. Let me just say one more sentence real quick, and then I'll take the question. So A, you start with a problem, and then B, what happens is you let the symbolic engine run everything it knows is true. If it got any of the correct one, it's solved. If not, it runs the LLM, and the LLM says, add one thing, and then you run the symbolic engine again. And you keep doing this over and over and over and over again. So this is, I didn't love this picture, but this is pictorially what I just showed you on the last slide. All right, please, question.
Yes, hi. The question I have is that when they run the symbolic engine to see if, given the, the current premises, they can get a closure or not. Do they run it on all of those top K?
They don't merge the K. They run each of the K separately in parallel.
Sure.
Yes.
Yeah.
So they are doing 512 closures every time around this square.
Okay. If any of them match, then it's solved. If not, then they pick the best one, the toppest of the top K.
No. Then the 512 all go back to the LLM, and it generates 16 further steps, up to 16 further steps. And then from all of those, it chooses the best 512 based on probabilities, right? And then it does the deduction closure on the next group of 512. That will all be one bigger than it was last time.
So at some points, you can have 512 times 512 things, like a batch of that big. No?
No, the way beam search works is you create a whole lot of things, but then you throw away everything except the 512. So yes, if it were just a tree, it would combinatorially explode. It would be 512, and then it'd be 512 squared, and then it'd be 512 cubed. But you prune it. That's the beam search. You prune it to just the top 512 after you've done.
But you said that the 512 are sent back, and then for each of them, another 512 is created, but then they are cut back to 512.
Yes. Okay. Before you give it back to the symbolic engine.
Okay, so you always give 512 back to the symbolic engine, but after you do that, like your next batch is going to be 512 by 512 that you give to the LLM.
No, you always give the LLM 512, and you always wind up with 512. That's your beam width.
Okay, I'm just repeating what you're saying, and at some point you say it's like 512 and then 512 and then you prune, but then you tell me that no, it's not that. So, but
you prune as you go. You keep pruning as you go. So that's I don't know the exact details, but in a regular beam search,
I'm with you. This beam search has always been a little bit,
Yeah. So let's just use a simpler number. Let's use beam search 3. Okay. So beam search 3, you've got 3 candidates, and let's say you say I'm going to add another token to the first one. Okay. So you add another token there, and so now basically,
well, I don't think you do them sequentially, right? I mean, you can as well send all the 3 to see what you get for each of them, right? And then you prune. In your batch, you send all of the 3. And for each of them, you get maybe 3, and then you cut them back to 3. So out of the 9, you get.
So that's, yes, in the actual implementation, you might do a little bit more. You do it with parallelism, okay?
Sure.
But canonically, okay?
Yeah.
Let's say you're doing beam of size 3. So you start with your best of the 3, okay? And you add one more token, okay? You look at 3 choices for adding one more token.
Mm-hmm.
Okay? It is possible that all 3 of those will beat completion 2 and completion 3. Right? Probably not, but it is theoretically possible. Okay? But the point is, once you add one more token and you look at 3 choices, you now have 5 choices. You have the 3 new ones from path 1, and you have the 2 old ones from path 2.
Okay.
Or something like that. Okay? And you could immediately trim it back down to 3.
Okay.
So I don't know exactly. Yeah, you're right. I don't know exactly when you do all the trimming and stuff, whatever. But yes, the point of beam search is you don't want it to expand too much. You try to keep it trimmed frequently.
Yeah. Thank you so much. This was really helpful. Thank you.
Yeah. Yeah, and I gotta admit, like every time I've talked about beam search, it's like with 3, with 5. I've never seen 512. So you actually may be right. Maybe you in parallel expand all of them by 512, and then you have
But then
whatever
that's
that is, 250,000 things, and then you pick the top 512 of that. That's a pretty expensive beam search, but it
yeah.
is possible.
So it makes sense to somehow do it, more
Yeah,
sequential.
yeah. I think it's better to do a little bit of proving
Right.
it. Yeah.
Great. Thank you.
But either way, even if whether you do it super cheap or you do it super expensive, you start with 512 and you end with 512. And then the new 512 that are all one more object, one bigger, will then go to the symbolic engine. And the symbolic engine now is going to end up reproving a lot of things that it probably proved the last time around, because those got thrown away as soon as you said, I didn't solve the proof. Okay.
Right.
But that's where, remember, they said usually it ran in a few seconds. So
But did they use any caching by any chance so that
no, not for this. Okay. And yes, I'm sure you could performance optimize this, that, but if it takes you a few seconds, it may not be worth it. So they said that they had whatever system with a whole bunch of cores, and they had,
Sure.
I don't remember, it was thousands of workers, so that they could just in parallel do all of this symbolic
Google, right?
deduction stuff.
Okay, great. Thank you.
Yeah. I mean, it wasn't like a massive system. I think it was a system with like 4 GPUs and a pretty heavy CPU, because the symbolic engine doesn't use GPU. So they wanted like really good CPU on this box too. Yeah, go ahead.
Yeah, sorry, I was under the impression that if it wasn't solved, you would feed like the problem and the number of steps that you took up until that moment to the language model, and then you'd add in another step. Is that not how it works? Or
So the beam search is where you do a whole lot of things in parallel, okay? But let's just pretend, let's simplify it to beam size 1, okay? So without the whole parallel business, you start with 3 points A, B, C, and the LLM says add a point D here. The symbolic engine then looks to see everything it can prove with A, B, C, and D. If it finds the conclusion you want, then the proof is solved. If not, it goes back to the LLM, and the LLM says, well, add a point E over here. And then it goes back to the symbolic engine and says, let me see everything I can prove now that I got 5 points. All right. And if it doesn't solve it, then it goes back to the LLM. The LLM's like, well, what if you add a point F, but I'm going to have a condition on it. F has to be added such that AF is parallel to BC. Then it gives that to the symbolic engine, and it tries. And it just keeps doing this. And then like there was one proof that took 247 repetitions of the LLM before it actually got to the end.
okay, so it does sound like what I was thinking. So every time you would feed the LLM a bit more, you would tell it where you got to. Like the input would grow incrementally.
Yes.
Yeah.
You are whoops, too far. You are concatenating. So the first time when the LLM says add a point D, then if that doesn't solve it, the next time you see the LLM gets it, it says, here's a problem with points A, B, and C. You're trying to prove blah, blah, blah. We added a point D. Then it's going to do its completion of what next. And it says, oh, add a point E. And then on the next pass, it's going to get a longer prompt that says, prove blah, 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 add a point D, add a point E, now what? Make sense?
Okay. Yeah. So sorry, just like what was that point? Like that I think on the last slide that you might have misread something, and then like how did is that unrelated to? Because I just got a bit confused when you said that.
When I first read the paper, I didn't realize that the symbolic engine might prove thousands of things once you give it all these points, all these facts. And so if you have all these facts at your disposal, then trying to sort of see like what next you should add, maybe you can get some good intuition about it or whatever. But I was mistaken, because the LLM never actually sees anything that the symbolic engine outputs. It saw it in training, but in inference mode, it never sees anything from the symbolic engine. It's just living
Okay.
in its own little universe, saying, add D, now add E, now add F, now add G. And it doesn't know. All it implicitly knows is if you keep asking me to add points, then we must not have solved it yet, so to
Okay,
speak.
so it just knows that it just knows what it's done, what the steps have been so far. I think that you
Yes.
described, and implicitly it knows if you're asking, and then it does. It
Yes.
solve it. Okay, all right.
Yes.
Thanks. Yeah.
And then
Beta had a question. Yeah.
Then the beam search part is where you basically let the LLM do 512 suggestions in parallel and you try all of them. And then if none of those solve the proof, then you let the LLM try another 512 suggestions. And this is where Vita and I were talking, like, I might have gotten it wrong. I'm not sure exactly how the beam search works, but the bottom line is at some point you let the LLM do completions and you only send the 512 best ones to the symbolic engine in the next round. Each time, the symbolic engine's only doing 512.
Okay. Thanks.
Yeah. Actually, you got a hand raised, so I'll do you second.
So the question I have, the example that had taken 240 steps, all of them were necessary, right? It wasn't like some of them were spurious or something, right?
Yes, they actually have some hidden things where they like verify, look for extraneous things and whatnot. Yeah.
But when during inference, it may generate perhaps stuff that they don't get used at the end, right? It is possible.
Yes, yes. In fact, that definitely happens.
Okay.
Like it suggested add points A, B. You start with A, B, C. It suggested you add D, E, F. It turns out you didn't need D or E. F was the key thing you needed, but it never thought to add that earlier. So you did it in 3 steps when you could have done it in 1. That absolutely happens. Yes.
Okay. This is so brute force in certain ways, like the 512 expansion thing.
That's why
all
I
of
was
them with the symbolic engine.
I agree with you. That's why I was not terribly impressed with this paper the first time I read it. But I will say the fact that the LLM doesn't get to see most of that brute force, once I realized that, then I was a little more impressed because the LLM is in its own little vacuum chamber. It doesn't know any of that brute force. It's just saying add D, add E, add F, add G.
How do we do things? I mean, when we try to solve these types of problems, we learn something from the path that we took and didn't take us anywhere, right? So I wonder if, I'm saying the same thing that you're saying, that, would have been nice if we could, utilize that.
Oh yeah. So I liken this to, do you remember Deep Blue when we first had chess playing computers? I don't think Deep Blue did anything very machine learning-y. It was just a fast enough computer and it had, I think, an algorithm for scoring chess positions, right? And it was just a fast enough computer that it could calculate millions of possible future moves and pick the best one. It didn't actually know strategy, I don't think. It was just brute force, what we're talking about here. This has a lot of brute force to it, but the LLM is still kind of cool.
You never know if it's actually still brute force, right? Because
yes, if you think about it, right? Like I tried looking. I don't know how many different things it could tell you to add. Okay, but
you said
to the extent that that number isn't that big, then this really is just full brute force, right? To the extent that it got to suggest 512, but there were, let's say, 50 million things it could have suggested, then it's a little more impressive because it's like 512 out of 50 million is still like 0.0001%, right? So I just don't really know exactly what the space looks like.
So when beam search is done, is it like, do they continue until there's end of premise token, or do they do the beam search per individual token?
So the max depth is 16. So they will only let the LLM construct 16 more points, and then they'll halt the beam search and they'll just take the top 512.
Okay. But then, okay, I see. So then because you said the dictionary is around 512, but this is like more like 512 times 16 or whatever you said in terms of complex.
Yeah, but yeah, so the individual tokens, there's whatever I said, 600, 500 of them, but any premise is multiple tokens, right? So remember, like this one, construct a point X so that ABCX is a parallelogram. That's probably 6 tokens, right? Add X is probably 1 token. ABCX is probably 4 tokens.
Right.
Is a parallelogram is probably 1 token. So it does take a trigram to define at a point X such that ABCX is a parallelogram. So if you think about it, even with a vocabulary 600, there's a lot of trigrams. Or sorry, this is a 6-gram actually, technically. Yeah. But you get the gist of it, right?
Yeah, great.
Yeah. All right. Thanks for your patience. Thanks for waiting, Roger.
So I think my question is kind of along the same lines. Intuitively to me, it would seem like suggesting the next point or a point to add would be complemented by having the knowledge of how to solve it. And I'm kind of surprised that they have a separation of the symbolic engine from the language model that's doing just the suggestion, symbolic engines doing kind of the proof. And I'm just wondering, did they say anything about that, justify that? Or is this more like kind of the AlphaGo, AlphaZero thing where it's just this was the first step and eventually they would use the engine for the entire proof?
Yeah, I think this is just the first step. And I didn't notice them. There could be there's something, a sentence that I missed. I didn't notice them saying anything, but once I kind of looked at it in a little more detail, I realized if the symbolic engine has a closure of 20,000 things that are true, a reasonable LLM cannot fit that in its context. Even if each of those is only 3 tokens, you're still just talking about hundreds of thousands of token context.
Yeah, although I could imagine an LLM being selecting the context better, right? That it doesn't have to look at all 20,000 if it just picks the 20 that you need.
Yeah, and we have tricks, right, that we use where we compress things or whatever. But yeah. Okay. No, you're right. I think they might think that that's sort of the next thing. This is a Nature article, so it doesn't really have like next steps as a section. Although a lot of papers, the next steps is pretty not very filled out, right?
Thanks.
All right. So here's the proof workflow, and in here you can actually see I believe these little parts here under D and under F, this is the actual string tokenization that was used in this model. So, so the LLM is outputting construct, which is probably a single token, right? Construct D, midpoint BC. And so that's saying add this point, but specifically add it right here, halfway between the two. And then when the symbolic engine does stuff, it's saying, I know AB equals AC. I now know BD equals DC. Blah, 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 blah. And I guess like angle is actually a token, the angle system. And so you can see it's got certain things like the concept midpoint, parallel, whatever kind of stuff. So this is what if you actually saw the strings going into the LLM, this is what it would look like. All right. So what were the results? we're a little short on time, so I'm not going to go too into it, but there are these computer algebra techniques where you can take the facts and you can convert them to special polynomials. Um, and then based on like the relationship between the polynomials and the roots of polynomials, you can sort of like see whether or not something has a root or not is true. So that there was this way you can do it with Grobner bases. Um, but then more recently, there's this Wu's method, which was like state of the art. Unfortunately, when you do this polynomial trick, the only thing you get is true or false. You don't actually get the proof. So, and also apparently these things become massively huge in terms of like uh, uh, um, memory and running time, whatever. So I can't remember what they said, but they said like there's some proof, it wasn't even like a huge one, and it ran for like a month on the computer, and then finally it output true. So you're like, okay, this theorem is true, but I still don't know why it's true. So then they did a bunch of stuff. They said, well, can this symbolic deduction engine do stuff by itself without needing the LLM? What if we use GPT-4, just native GPT-4, just trained on whatever OpenAI trained it on, right? To get it to suggest what points to add. And then like we'll goose it a little bit and help GPT-4 know some things or whatever. Um, anyway, so these are the various things, and the best that they could do is 18 out of these 30 problems since 2000 that they were able to solve. Um, and so they had some handcrafted heuristics of like good types of points to add and whatnot. They got to 18. So their model solved 25 out of 30. We'll see in a second that this is just below what the average gold medalist at the International Math Olympiad. So this is not the gold medalist at the US Olympiad. No, those are the guys who actually made the team but didn't necessarily win the Olympiad. It's the best performers from all the countries got gold medals, and this was their average on the 30 problems over the years, right? If they just did training on the 9 million instead of the 100 million first, it dropped from 29 to from 25 right to 21. If they trained on all 100 million problems but didn't do the fine tuning, that wasn't as big a deal. It dropped from 25 to 23. If they gave it 20 million instead of 100 million training set, it dropped from 25 to 21. And if they lowered the beam search from 512, which I think some of us thought was kind of brute forcey, they tried different numbers you can see in the paper, but lowering it all the way to 8, which I think is a much more reasonable beam width, then they got 21 out of 30. So these are pretty good performances in these sort of ablations. Not quite as good as the 25, but it's still, all of these would have beaten the baseline of 18. Yeah, sorry, Alan, you had a question.
Like if you go back to the last slide, it seems that if a person were to solve like a maths problem, like the one, like the simple one here, we'd one of the things how we would, come up with steps of reason to try is we'd kind of look at kind of global or superficial aspects of the issue and that of the problem, and that might provide some guidance about things to try. Like for example, if we had some maths problem with numbers, we might try putting in extreme values and see where that gets us. Or in this example, we might just notice, oh, it's symmetrical, and that might, that an isosceles triangle is symmetrical, and that might prompt us to try constructing a midpoint. And it seems that using that kind of intuition to guide, what steps to try is somewhat what the language model is kind of there to do, because there's just so many different actual possible things, next steps you could try. However, we don't necessarily know that the language model is actually does exactly what the human intuition is doing, or something like that. It could just be it sees some correlation between like an equal sign and constructing midpoints and things like that. I think
Yeah.
that's just the nature of all sort of elements.
Yeah. So let me just say back your comment. Okay. They're saying that the language model was smart enough to make reasonably good suggestions for new things that you need to add, such that it could prove more things than any other computer has ever proved in geometry. Okay. But they're not calling it AGI. Right? They're not saying that now AlphaGeometry is going to go and prove things that math professors can't prove, right? So I completely agree with you. And they're not claiming that either, but they are saying like, hey, look at us, this is way better than anything anybody's ever.
Yeah.
So before they worked on this, the best anybody ever did was 10 out of 30. And then they had some other things. Um, uh, um, I mentioned it very briefly, but this AR is this analytical reasoning, and so the symbolic deduction engine would just deal with things like equality and stuff like that, and the analytical one could actually deal with actual numbers, like I think the idea that uh, something might be double of something else is something that it would be able to do, and so there's a whole thing that they did how to construct this as systems of linear equations, and so then they were able to use Gaussian elimination and stuff. It's in the methods at the very end if you guys are curious about that.
Yeah. I can imagine the engineering feat managing all that beam search and branching trees and the LLM pipeline and all that. Yeah.
Yep. All right. So in conclusion, just sneaking in under the top of the hour.
Did Vita still have her hand up?
I thought it was just a leftover from before.
Okay.
So AlphaGeometry, it's solving this one subset, Euclidean plane geometry, better than any computer baseline before, better than any computer baseline that they could build without building AlphaGeometry, better than GPT-4, better than Symbolic plus GPT-4, any of those. And the silver medalists over the last couple decades, they averaged 22.9 correct on these 30 problems. The gold medalist averaged 25.9, and they got 25. It's only 30 problems, and there's not other International Math Olympiad problems you can sample from. So we don't really know what the standard deviation is on AlphaGeometry. We don't really know if it got lucky and it did 25 or 30, or it got unlucky, but nevertheless, it's way better than anything ever before and almost as good as the average gold medalist, which is like the best, right? Like the best 18 and under mathematicians in the world for the last 25 years. That's still pretty cool result. Even if it's brute force, it's still pretty, just like when Deep Blue beat, right, Kasparov or whatever, like that's still a pretty impressive result, even though it was just brute force. So again, the data scarcity was arguably the biggest problem they had, because we know we can train deep neural networks, but deep neural networks require a lot of data. Linear regression doesn't require a lot of data necessarily. Deep neural networks require a lot of data. So they had to come up with a way, and they ended up generating 100 million, mostly unique. They deduplicated, but maybe not 100% perfectly. 100 million unique proofs. And in their final solution, they use both the symbolic engine and the LLM that alternate. And so they call this combination neurosymbolic. I don't know if other literature uses neurosymbolic in a slightly different way. Like if the LLM were doing deduction on symbols, that's sort of a different thing. This is really a completely separate symbolic system that has no machine learning and a completely LLM system that I don't know if it really is doing symbolic reasoning. And then finally, I didn't mention this, I maybe should have said it earlier, but because they used a search style technique, the proofs that it does, right, where it's like step by step, add this, and then the symbolic engine does its thing, it's completely human readable, right? Because you basically say add a point that makes a parallelogram, and then the symbolic engine says, by blah-blah theorem, we now know that these things are parallel. By blah-blah theorem, we know that these two angles are equal. Okay, now add this other point. By blah-blah, so it's that's the nice thing is it's not just proving that the theorem is true. It's actually a very human readable trace if you just look at the steps that it took. So they have a blog post. I don't know that it's that different from the article. They have a repo if you want to take a look at the code. They mentioned, so in early work, this is this model called GPT-J. I recognize Ilya Sutskever as the second author on this. So this is from 2020, which is pretty early. Like, I don't know how GPT-2, whatever time frame, right? They built this. And then if you're looking for something more recent, like just a few months ago, there's this article called Lemma. And it's a pretty current article talking about proving general mathematical things. It's not limited to geometry. Yeah, Roger.
Yeah, question about the proofs that they generated, synthetic proofs. Did they talk at all about, so I can imagine creating, I have 100 million proofs. A lot of them could be kind of trivially different than each other and not necessarily add a lot of guidance for a logical deduction through the proof. Did they talk at all about pruning that or filtering for quality?
I think there may have been some further details on how they did the deduplicating that I didn't bother to read.
Okay.
But yeah, they did. They clearly said that they had some deduplicating because it was something like 300 million proofs that they generated, and then after deduplicating, they were only left with 100.
Okay. Okay. Thanks.
Thanks.
Question on the slide that had that midpoint. So I'm trying to, yeah, this one, thanks. I'm trying to understand the 512. So does it construct, where it says construct D, midpoint BC, does it do 512 of those and they've shown only one of them?
Exactly. So you get your inputs that says you have A, B, and C, blah, 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 blah. Okay?
Mm-hmm.
So you get 3 points, you get a fact, AB equals AC. Length of AB equals length of AC. Okay?
Mm-hmm.
Then the symbolic engine goes and it says, based on this, I know that angle ABC equals angle ACB.
Right.
Well, actually, no, well, whatever. But it has different things that it knows are true, okay? And then it says, I didn't get what you wanted as my final answer. Okay?
Right.
So then you say, okay, LLM, what do you want to do? And it says, construct a point D that's the midpoint of BC. And then you do another inference pass with a different random number seed. And it says, oh, why don't you construct a point D that's halfway between A and C?
Right.
Okay. And then you do another pass and it says, construct a point D such that it's on the line that halves this angle ABC.
Mm-hmm.
Okay. And then you do another with a random number seed and it says, construct a point that's at the, what do you call that? That's like the center of gravity. I don't know what it's called. Epicenter, whatever. But
Orthocenter.
Orthocenter. Okay, right? And then you do another random seed that says, construct a point that would be the center of a circle if you inscribed a circle inside this triangle.
Mm-hmm.
And another one says, construct a circle. Don't actually add a point. I want you to construct a circle that circumscribes this triangle ABC.
Mm-hmm. Mm-hmm.
And then it's like, construct a point that's on along the infinite line AB, but that is equally far from A in the opposite direction as B is from A. You know what I mean? There's like zillions of things you could do, right? And if you do 512 of them, you probably get duplicates.
Right.
For different
so then, so one of the 512 is this thing here, right? And
yeah,
then
so
they
this is one of them, and you're going to test all 512 of them.
Right. and you're going to feed all of those 512, like you said, to the symbolic engine. And then in this case, one of this 512 ended up solving it completely, right? So
Right.
I think
And
the
then you
next
throw
two
away the other
lines,
511.
yeah, so the next two lines, I think, basically are
Yes.
both from the symbolic engine.
Yes, that's right. This is the symbolic engine. Actually, this construct is also the symbolic engine because it needs to know that.
So what's coming out of the LLM?
Yeah, it's not exactly clear, but I think the LLM shares the same language as the symbolic engine because remember, it was trained on symbolic engine output.
Okay. Mm-hmm.
In the pre-training, right? The 100 million it consists of things that look like this.
Mm-hmm. Yeah. And so basically, like if you look at the F solution,
the more complex one.
Yeah, so they would have had to there'd be 512 in each step, and they would have had to go through it to pick the right combination to show us here. Right?
Yeah, because I mean, look at this, right? Like construct O2 midpoint of HQ such that BQ is parallel to O2D, right? This is like a pretty complex set of conditions for just adding one point.
Mm-hmm.
And so you can imagine there's just zillions of other possible,
right,
things you could do.
Interesting.
And actually, I think maybe as opposed to doing 512 passes, I think what you do is you actually look at the top 512 logits for each next token. But each time you add a token, you keep trimming it 512. You know what I'm saying? Because actually, it doesn't make sense. If you just do different random seeds, you might just get the same thing over and over again. So sorry if I've misspoken on beam search. You can look at Wikipedia and probably get a better explanation than I gave.
But there's some process that generates 512 candidates essentially,
Yes.
right? And
yes.
then at each step, and then they had to go and backtrack. So if you look at the last one, then you say, okay, one of the 512 is the right one. You don't know that, right? So somehow.
Yeah. I mean, if one of them turns out to be correct, then the symbolic engine is going to say, pick me. I'm the one that found the solution.
Right. Yeah, I'm just trying to think from an inference perspective. I guess it would still work. You could pass it through the symbolic engine and it would tell you.
Yeah. So basically, if the symbolic engine sees the conclusion that you want, then it basically yells solved. And then as the programmer, I can tell you they did this stuff where they had all of these parallel worker threads or whatever. And so then when you get the signal from one of them that says, hey, I solved it, then basically somehow the parent process, right, probably then signals all the other thousands of threads and say, hey, you guys, we already solved the problem. I don't need you anymore. Go away.
Right. Yeah. And then I guess you could go back, it's like a DAG, and you go back through it to figure out your steps.
Yes. So ultimately, you have some kind of, this is a very small DAG, but you have some kind of DAG that shows all the steps that you followed in order to get to your conclusion. And you can just walk that DAG. And each DAG is human readable because each DAG is very much, at a point that's the midpoint on here, create a triangle, create a circle. We now know that these two things are equal. Oh, now that I know those two things are equal, now I want to make a new triangle.
Yeah. Cool. Thanks.
Yeah. Thanks.
So Ted, it's easy if you get you add a point that solves it, but if you don't, how would you do pruning? Like, how do you judge the value of the different 512 different solutions?
You're talking about inference now?
Yeah.
Right? No, at inference, you don't know anything. That's why I'm saying I was a little bit more impressed with the LLM once I realized the LLM is it's in its own little vacuum chamber. Just saying, add an A here. That didn't solve it, add a B here. That didn't solve it, add a C here. That still didn't solve it, add a D there. It's blind.
I'm just saying in a beam search, you throw away ones that aren't as good, right? And you keep a smaller number of ones that you're
Right,
focused on.
But
So
good
there's
is
no
has nothing to
beam
do with
search.
geometry. Good just has to do with the logits of next token prediction are the highest.
oh, okay. Okay.
So
Gotcha.
like when you do beam search on language,
Yeah,
right?
yeah.
You say
Yeah.
the boy hit the whatever, and so one completion is ball over the fence,
Gotcha.
ball to the shortstop.
No, you got it.
The
I understand now.
right, and so then you're judging sort of the probability of the entire completion, ball over the fence, ball to the shortstop. I don't know what else you hit. Hit the punching bag, and so then you say of those complete completions, not just the one token, but the full completions, which had the highest probabilities, and then you throw away everything but the first token, so to speak. That's the gist here.
All righty, are we done, Ted?
We are
Do you have
done.